So what we're looking at in this video is the basics for your electrophilic addition reaction. It's kind of intended for organic students either as a primer for the first semester student or as a review for the second semester student. Part of this video is a little bit weird where we're going to kind of run off the rails with kind of my interpretations of trying to see patterns within the mechanistic reagents for our electrophilic additions. To start it all off with, what we're starting with is a non-polar pi bond. So we're looking at typically alkenes, so just a carbon-carbon double bond. But these same reactions will also apply to alkynes. There are some subtle things you do got to watch out for when you shift to the alkyne, but for the most part, the chemistry is pretty much the same. One of the reasons why the alkene chemistry is typically talked about after, say, halohydrin chemistry, with the carbon-chlorine bond, is that the chemistry is less obvious. In a carbon-chlorine bond, we know chlorine is more electronegative than the carbon, thus pulling all the electrons towards it, and we get this negative positive. So what we're seeing is this hetero charge. The problem with the alkene is there's no real hetero charge. We're talking about a carbon and a carbon. So the electrons don't really seem to have a reason to shift one way or another. But if we go back to understandings of molecular orbitals, the reason why the pi bond is so much stronger is that those two p orbitals are in alignment with each other, which means the electron has the ability to jump, between one orbital and the other. That ability is what's generating our polarization within this. We could look at the system where the electron doesn't jump, and we'd be looking at a radical system. We're just not going to worry about that for this video. So if the electron jumps around, there end up being two possible states, shown here as blue and red. These structures are resonance contributors to the parent, more accurate structure. So if you were asked to draw a Lewis structure for an alkene, what you should be drawing is in black, minus the p orbitals. But if you want to understand something about how the alkene reacts and changes further on down the road, you should be looking at these resonance contributors. Within those resonance contributors, they're going to help you dictate what is known as the regiochemistry. And that regiochemistry is the location of where our reaction is going to happen. Where do we have our negatives and positives? So when we look at these two resonance contributors, you should be able to tell me that one of them is more stable than the other right about now. So hopefully you went through and acknowledged that the blue one is more stable than the red one, and that is true for a variety of reasons. The easiest for most people is the carbocation is located at the more substituted position. In this case, it's a tertiary. We could also evaluate the anion. The anion is at the more stable position, primary. If you need help understanding the stability differences between those, I would recommend you go look for the substrate video, which maybe I'll try and get linked in here. So, to our electrophilic addition reaction, the basics of it is our alkene acts as an electron source because we have that pi bond. In this case, those electrons we would expect to kind of sit out on that carbon as its reactive structure. That then needs to react with something positive like a Lewis acid. That Lewis acid will likely need to be stabilized by some kind of Lewis base. And so the net result is that we end up losing the pi bond and replacing it with two new sigma bonds. We get a sigma bond to our Lewis acid, and we get a sigma bond to the Lewis base. As we've talked about in my classes at least, the Lewis definition is really broad. So what we might do is narrow it down. If our Lewis acid is now better referenced as a Bronsted-Lowry acid, we can look at the quote-unquote electrophilic addition reactions with acids. And that's what we're seeing on the lower left. And we'll get a slightly different system to evaluate, and it tends to be a little bit easier for students to process because it's just a step above the acid-base reaction. If instead it's not a Bronsted-Lowry acid, well, now what we're doing is shifting the Lewis acid and calling it better as an electrophile. So anything that can accept electrons that's not hydrogen. And as soon as we make that shift, we now get a whole nother system of reactions, some of which mirror what we see for acids, some of which become a lot more complicated. And that's usually where we tend to lose students, is in that electrophile section, because virtually everything looks unique. Okay? So let's look at the simple one, pi bond as a base. It is the simplest reaction, and it is composed of two mechanistic steps, or elementary mechanistic steps. The first one is technically an acid-base reaction, though we can run into some kind of definition issues because it's not really an acid-base. According to our textbook or CARTI, it's better known as an electrophilic addition because of the loss of the pi bond. Okay, but it's really just an advanced acid-base reaction. We're taking the electrons from the pi bond, we share them with our acid. This hydrogen we would expect to be H+, because whatever this A is something that's withdrawing electrons from that hydrogen. That could be a variety of different atoms. So hopefully you would have come up with maybe Br-, Cl-, I-, all of those being our strong acids. We could have also seen maybe OH-. The problem with that is that's not a strong acid, which means the H+ isn't strong enough to react, and the reaction just kind of dies. Okay, it doesn't go anywhere. So when we're looking at this, we need a strong acid because that pi bond not charged enough to really do much on its own. Once we've neutralized that acid, we can then go through and look at our intermediate. Notice that in our intermediate state, we have a carbocation. The location of that carbocation is dictated largely based off of the regiochemistry, looking at our resonance structures. We want that most stable carbocation. Once we have the carbocation, we can neutralize that with the conjugate base of our strong acid, that A-, and that can come in and permanently stabilize. And we'd end up with our final product, the full addition, okay, where we've added hydrogen and A, okay, our conjugate base to this. So overall, our reaction, we have a loss of a pi bond, so we're looking at an addition reaction. Once we classify it as a particular type of reaction, that can help limit the number of reagents that we need to be thinking about if we're being asked for reagents. This also helps us limit in a multiple choice coming up with potential products. If I know the reagent is an addition reagent, I need to do an addition reaction. So it can simplify how I think about what I'm trying to solve. The next part that becomes a lot more complicated is now looking at the structure and mechanism. So those two things are the pieces that are going to dictate what's happening with your stereochemistry, which is the spatial arrangement. Okay, and I would argue it's pretty much just the spatial arrangement of the hydrogen and atom A. Okay, and what do I mean by that? Well, we could have the hydrogen wedged and atom A wedged. So are they spatially on the same side of that sigma structure, or are they on, say, opposite sides? So that's our stereochemistry. Where's that spatial alignment? The regiochemistry is the numerical location. And this is where I said you can go through and use resonance to dictate that. With the structure shown above, there really isn't a difference. Whoops, that was not the button I wanted. There isn't really a difference on how we number it. So we go 1, 2, 3, 4. In this case, A is always going to go at position 3, H is always going to go to position 2. But if, say, H went at 2 and A went at 4, or some other kind of sequencing, that's now a regiochemistry. Okay, so that's the numerical location in that backbone of where we're placing those groups. Okay, so let's get a little bit of mechanistic detail with the energy diagram in, because I said that was important. So what I want you to do is take 1-methyl cyclopentene nomenclature with hydrochloric acid. So you should be able to come up with all the possible mechanisms and products. Keeping it simple, ignore stereochemistry, include regiochemistry. So consider regiochemistry when you run through your mechanism. And then you should be able to go through and draw an energy diagram for both mechanisms. So there's a hint. And we'll give you a second there. Okay, now that you've had your second, if we look at 1-methylcyclopentene, there's our cyclopentene, there's position 1, and there will be our double bond. If we want to react this with hydrochloric acid, we're taking the electrons from the pi bond, reacting it with the hydrogen, and the electrons go to the chlorine. This is where we're going to end up with 2 results again. Okay? Both cases are going to result in a chloride, okay, a Cl-. The trick is going to be, where do we place the hydrogen? Our arrow, because it's starting at the pi bond, doesn't dictate which carbon the hydrogen comes from. So, or which where the hydrogen goes to. So that information is dictated by what we draw as the answer. So as the chemists, we have to make that decision. Okay? In this case, I'm going to make the decision that the hydrogen went here. Okay? The other piece that we have to remember is that those electrons are what are making that pi bond. Okay, so if we color that in green, well, those electrons were shared between 2 carbons. One of those carbons has now formally lost electrons. It needs to be positive. Okay, now the reaction can continue, and we'd end with our final product with the chlorine attached. I said you can ignore stereochemistry, but if, say, we weren't going to ignore stereochemistry, we have to consider how that chlorine reacts with the positive charge, and we'd also have to consider how the pi bond reacts with the hydrogen, being wedges or dashes, so above or below the plane of the structure. Since we'll see that in a little bit, I'm going to let you stew on that. Okay, that gets us our mechanism, okay, or one of the mechanisms. Hopefully, you at least came up with one, and you came up with not the one I just drew. Okay, so there we go, nicely drawn out, same deal, we've got our mechanism. When we look at our energy diagram, okay, we're going to start with our reactant, our alkene. Because we don't really know necessarily where we're going to go, we'll pick kind of an intermediate space. So we'll put it middle of our energy diagram. Okay, now deciding between the intermediate and the product. Okay, if we only focus on the organic compound, our intermediate is a carbocation, which is higher in energy than the starting pi bond. So we should go up in energy. The product, our final product out here, isn't charged, so it should be lower in energy than our intermediate, and it should be lower in energy than the starting material, because the starting material had a pi bond, and the product doesn't. So we would end up with an energy diagram that looks roughly along these lines. Okay? And we've now described how this reaction could work. Okay? And that's kind of neat. Where the energy diagram becomes more powerful, though, is if we bring in the other mechanism that you guys went through and did. Okay? That other mechanism shown in red up above, if we dropped in its energy values, we could see something along these lines. Both reactions are starting at the same alkene energy, and they go through to make our products. So there's some interesting things to note. First one I'm going to note, the red product is higher in energy than the blue product. Okay, well, why might that be the case? They're both sigma bond structures, so why would we see a difference? Well, in the red one, that chlorine is closer to the methyl. That generates a steric interference. Steric interference, which increases the energy of that structure. It's a relatively minor effect, so we're not showing a huge difference down at the bottom. If we go through and look at the intermediate, you'll notice there's a significant difference in energy there, and that's because we're looking at charged states. And if we go through and evaluate those two states, the blue one is a secondary carbocation, the red one is a tertiary. The tertiary carbocation is significantly more stable than the secondary, and so we see this large difference in energy in our intermediate. If we now want to go through and decide, well, which product should we get? Okay, well, one option would be just looking at the product energies. And if we just look at it from that thermodynamic point of view, we might say, well, there's no difference. We would expect equal amounts of both. And it turns out we get primarily the red one. okay, which does seem to run kind of counterintuitive because if anything, it's the higher energy of the two. Okay, so why do we see the predominant form of the red one? Well, when we run a reaction, we have to proceed through the intermediates. Okay, and if we look at the red arrows, or red line, what happens is its activation barrier is significantly lower than that for the blue one, which means that pathway happens more likely. Okay, so as it progresses, we expect to see a lot more of the red one. Okay, because we're looking at an intermediate stage for this product, we reference this as the kinetic product because it formed first. The blue product is now the thermodynamic product. In this case, there wasn't much difference in energy between them, so there isn't a huge thermodynamic favoring here, but there is a slight favoring for that thermodynamic product because it's lower in energy as a product. Unfortunately, because of that intermediate state, we don't actually get to make much of the thermodynamic product. Okay? So when we go through and look and think about energy diagrams and charges and structure and all of these pieces, we can come up with explanations for why these things happen. Okay? Interestingly enough, in roughly 1870, so before we actually understand what an electron is, Markovnikov noted that the red product formed predominantly. Okay? And that's where we end up with the Markovnikov addition rule, which I personally dislike because it's ignoring all of the structural chemistry that leads you to the answer. Okay? All that's saying is that the red one's formed. That's all Markovnikov could do. Make the red one. That was it. And we've now memorized that as a rule. It's not a hard and fast rule. There are exceptions. So we do have to take into other considerations that require a structural understanding. So let's just stick with the structural understanding. So my lesson kind of out of this is if you're looking at an endothermic reaction, you need to make the one that's the most stable. And when we look at our reaction for the reaction to progress two products, we have to make it through this very first step. This very first step happens to be endothermic because the product intermediates are higher in energy than the reactants. Okay, so if you see an endothermic state, you need a more stable structure. Okay, so think about stability. Our structural and stereochemical traps that we got to worry about is we have to think about how the reaction occurs and where. So when the reaction first started, we were talking about the pi electrons, so the electrons in that pi bond coming out to react with the hydrogen. Well, those electrons are in p orbitals. The p orbital occupies space both above and below the plane of the molecule, which means that hydrogen could be placed either above or below the plane of the molecule. That means there's two possible structures that could come out of that. Those two structures may be identical, they may be different. It depends on the structure you're working with. Okay? And so that's where you have to be careful. Because hydrogen is so ubiquitous, we typically don't see an effect at this stage. Sometimes you do. Okay? So the next step of the reaction was that the nucleophile could then come in and react. And the nucleophile needs to share electrons. We'll share electrons with what? We'll share electrons with a p orbital. Well, again, where is a p orbital? It's both above and below, which means the nucleophile could attack from above or below for both of these possible results, which means there ends up being 4 possible structures that could come out of that. Okay? So every addition reaction with a strong acid has 4 possible structures. Some of those structures are identical, in which case we would ignore that as a potential product. Some of them are different, are stereoisomers. So because of that, you have to be at least considering that. When we look at our overall reactions, our alkenes are achiral starting materials, and this means that the product must also be achiral. So if you go through and decide that one of these is true, well, then there has to be another one, because if that one is chiral, there has to be a counter achiral one to it, unless you've introduced some other kind of chirality, which we typically don't see. With the electrophilic addition with acids, it may or may not surface as a problem. If you see wedges and dashes either in your alkene or in your final products or Haworth projections, you really need to be considering these stereochemical traps. Okay, so now the real fun one. Pi bonds as nucleophiles. So these are strict electrophilic addition reactions, and they become a lot more complicated. When I go through and look at patterns here, what I see is that we're either looking at a situation where the leaving group is good or the leaving group is bad. So what we're addressing is the electrophilic species, not the pi bond as a nucleophile. If our leaving group is good, okay, that's one condition that needs to be true, but we'll also need to have a Lewis acid acting as a nucleophile, which takes a minute to beg the question, how does a Lewis acid act as a nucleophile? Well, alkenes did that, okay? And alkene is a pi bond. Well, if we look at the resonance structure for that, we could put a negative charge at one carbon and a positive charge at the other. We get a Lewis base and a Lewis acid. So alkenes do satisfy this kind of at least minimal requirement, okay, as a larger structure. But now what we're looking at is a single atom doing this. And that does become a bit more challenging, but it does happen. So mechanistically what happens is our electrons will come out to attack the Lewis acid. Because the leaving group is good, it leaves. Okay? Two big things need to be pointed out here. Number one, we said the Lewis acid is also a nucleophile. So the Lewis acid also has a lone pair of electrons. When the electrons came out of the pi bond, one of those carbons lost electrons. That loss of electrons means it became positive. Well, what could you use to stabilize a positive? How about some electrons? And so we get this kind of goofy looking three-arrowed system that tends to freak students out. Okay? But really all we're saying is that those electrons are trying to stabilize as quickly as possible. Okay? This will generate an even goofier three-membered intermediate or final structure, depending on stability. Okay? The big words that come out of this, you'll typically see the bromonium ion, but you could also see halonium, because that's now referencing all halogens, bromine, chlorine, iodine. Okay? And you could also see the mercuronium. Let's just say that's spelled right. A mercuronium ion. Okay? At that stage, we have goofy names, which means they probably aren't stable. They will continue to react with a secondary nucleophile. Okay? That nucleophile could be the leaving group. It could also just be another nucleophile. The nucleophile comes in, reacts, and we end with our final state. Notice there's a question mark there. That question mark really has to do with the stability of that three-membered ring. If that three-membered ring is relatively stable, we're done. We don't do another step with a nucleophile. If it isn't stable, then we do another step. Okay? Well, what happens if our leaving group is bad? Well, if the leaving group is bad, it can't leave on its own. But the Lewis acid has too many electrons, so those electrons have to go somewhere. Instead of those electrons going out to the leaving group and then disappearing from the structure, what they will do is immediately come back, okay, to stabilize that forming carbocation. This ends up with potentially larger ring structures. So this is where we get 4-membered transition states or 5- and 6-membered intermediate ring structures. This also very quickly places both the Lewis acid and the leaving group on the structure almost instantaneously. So that would then beg the question, do we need to go forward? Well, again, it depends what's on your structure. Okay, and so we'll look at a couple examples for that. So, big lessons at the bottom. The reaction is an addition because we've lost a pi bond, and that helps us predict the products as long as we can identify our pi bond It's regiochemistry, the Lewis acid, and the leaving group, or nucleophile. If we have those pieces, we're good to run. Okay? The next part is where those pieces are located, kind of our mechanism. So stereochemically, what is the alignment of the Lewis acid to our nucleophile? Okay? And we might also use that mechanism to help us predict something about the regiochemistry. So let's take a look at the three-membered transition intermediates. So how can we get a structure that is both an electron acceptor and donor? We already gave you an answer for that. Alkenes. Alkenes do this, but now we want a single atom to do this. So that single atom needs to have lone pairs and very weak bonds. So here's 3 examples. Okay? Take a minute to see what you can nail down for each of these. So that first one, lone pairs, yes. Weak bonds, yes. That bond between the bromine is actually fairly weak because the bromines are both very large and very electronegative. They don't really need to have that pairing, which means those electrons can shuttle one direction. By shuttling to that far right bromine, the far left bromine has lost electrons. We now have the positive and the negative. This satisfies our three-membered transition. Okay, that's where we're going to get our bromonium. Okay, well, how about the next one? Well, the next one, do we have lone pairs? Yes. Do we have weak bonds? Yeah, we have polar bonds. Those are weak bonds. Okay, those bonds would break with the electrons going towards the oxygens. Why would they go towards the oxygens? Oxygen's more electronegative. Fantastic. Which means we now have the same system. We have lone pairs and very weak bonds. But before we get too excited about that, what does that blue arrow generate on our oxygen? Well, a negative charge, more electrons. What did the red generate? Well, a negative charge. We needed a structure that was both an electron acceptor and donor. CO2 doesn't fit the bill very well. Okay? Those electrons don't match, so we aren't going to see a species that actually aligns to react with our alkene very well. Okay? So that one doesn't fit the pattern. If we move to the last one, we've got the mercury in the middle with our lone pair. We do have weak bonds. Okay? That weak bond is weak because of resonance. Hopefully you got that answer right. So the bromine and the mercury reagent are both characteristic reagents for your three-member transition state. Okay? Does it continue? Okay? Well, once we've done the reaction and placed that first atom on, do we continue to react afterwards? Well, that's going to come back to stability. Okay? And it's really going to be stability back to the nucleophile. So consider, if it's stable, stop the reaction. If it's unstable, then we should do a nucleophilic attack. If you're unsure, then do the nucleophilic attack anyway and look at that product. Okay? If that product is really, really ugly, then you probably shouldn't have done it, and it was probably stable to begin with. Yes, that's a bit wishy-washy, but if you got nothing else to draw on, you better pull from something. Okay, so 3 structures again. Take a swing at them. Stable, unstable, and take your guesses. In the first case, we've got stable. That oxygen versus this oxygen. Our potential nucleophile is that negative oxygen coming in and attacking. Well, we've got a negative oxygen versus a neutral oxygen. Negative is more unstable. Okay, your 3-membered ring is more stable than the nucleophile, so we're going to stop right there. Okay, there's no reason to continue forward. Okay, if we move to the next one, we've got the bromonium. Okay, so Br minus with our negative. Okay, attacking and ring opening. Is the bromonium unstable? Well, yeah, it's very unstable. It's got that positive charge, and I don't like bromine with that positive charge. So if I run that reaction, the result would be I get 1 bromine at the bottom, 1 bromine at the top, and all the charges are gone. Well, that result is more stable than what I started with. That's a good option. Okay, so I'm going to keep that one. Same kind of idea can apply with the last one. If you really don't know, run the attack and see what happens. We get a negative charge carbon. We'd get our nitrogen down here with that positive. Is that product more stable than what's in the red box? No. Because it's a no, don't continue. We stop there. Okay? So it's okay to be like, I don't know. Run a reaction. Find the electrons, find the positive, and put them together and see what you get. Okay? So, three-membered structure and mechanism. Based off of the mechanisms that we just kind of looked at, what would you expect? Okay, so first off, what is the difference between these products? Okay, and then based off the mechanisms, which one would we expect to see? Okay, the difference between these structures, A is what is known as the anti-addition, or the anti-product, and the bottom one, B, is what is known as the syn addition. These are very similar to cis and trans. You can't call them cis and trans because cis and trans applies to a pi bond. There's no pi bond anymore, so it doesn't work. Okay, but it's the same kind of concept. So we could call it a pseudo. I don't want to write pseudo. The top one, anti, is kind of like trans, so we'll write trans and cross it out. And the bottom one is kind of like cis, but we'll cross it out again because there's no pi bond. So those kind of concepts are applying. Based on the mechanism, which should we get? When we run the three-membered, we should probably see a majority of A coming out of this because we first form that bond with X as our three-membered ring. Y then needs to come in from the back side of that ring structure to break it open. Okay, so we should expect to see the anti-addition in a full electrophilic addition reaction with three-membered transition states or three-membered intermediates. Okay. Oh, and I apologize, we're still going, but we're almost done, I promise. Our 4+ member transition state and intermediate. For this subclass, we need a small leaving group. So take a quick look at these three structures. We already looked at the bromine. Br- is not a small leaving group. That's incredibly large. Okay. H- on the other hand, very, very, very small. That does fit our 4+ member transition intermediate. Okay, so this one is going to be a 4-member. We'll call it a 4+. Last one becomes a tricky structure to deal with, which is why it's actually up there. Our pi bond can come in and attack one of those oxygens, causing electrons to shuttle out. Okay, so our quote-unquote leaving group, okay, remember, this is where Mike went off the rails here, but our leaving group here is electrons. Okay, so is that small? Yeah, electrons are about as small as you can get. Okay, which ends up meaning we get this big cyclic reaction. The other oxygen comes out. Okay, and we form a 5-member transition. So yes, this reagent does fit the bill of the 4+ system. Our leaving group is electrons. That is by definition small. Okay. Depending on our connectivity between our Lewis acid and our leaving group, we may see different cyclic states. In the case of the 4, they're almost always transition states. If they're 5 or larger, we're looking at full-on intermediates. So we've got overall mechanisms kind of aligned here. Boron is your big characteristic marker for these 4+ member transition states. Boron has that large p orbital that's kind of empty, which is where the electrons can dump into. It then makes boron unhappy. It ejects hydrogen as electrons, which come back in. We look at the osmium, we're getting a similar kind of system. All of those oxygens are drawing so many electrons away that the osmium eventually says enough is enough, okay, and it starts to steal electrons from one of the oxygens. That makes the oxygen susceptible to a nucleophilic attack by the pi bond. This causes a big shift in electrons, and we can get another one of the pi electrons from our osmium structure coming out. Okay? And we'd end up with these two possible structures as products, and we've now done our addition. Okay? If we're now thinking back to our structure and mechanisms on deciding where our pieces should go, okay, we've already answered the difference between these products, but now A versus B, which one do you think should happen in these 4+ membered systems? Okay, right. So, well, in the cases that you just showed, Mike, we had X and Y connect on the same side. Well, yeah, exactly right. Okay, and admittedly, Mike wasn't thinking, because he's an idiot sometimes. Yeah, we get the syn addition. We get the other result out of that. It's not a big surprise. It's exactly what happens. We get our syn addition. Okay, those pieces now have to come in on the same side of that pi bond. Okay, so that's going to align our stereochemistry a little bit differently than if we had a 3-membered system. Okay, if we backtrack real quickly here, we look at those products, we see boron on the structure, we see osmium on the structure. That's ugly. Like, we haven't seen that before. Why are those there? And even if we looked in the book, those structures show up as intermediates, not as final products. Does it need to continue? Yeah. Okay. So you've probably seen these reagents already in your textbook, and you've probably seen they don't show up alone. When we see that boron reagent, it almost always is followed by a second step. Okay. Usually peroxide and hydroxide. Okay. The mercury reagent is almost always followed by a second step, sodium borohydride. Okay. This, while it has boron, is different than the BH3. Okay. Why are those two borons differently? We'll call it black boron and red boron. Why are those borons different? And then we've got the osmium reagent, which is unfortunately just gross, to be honest. Sometimes you'll see it with an extra thing, which I don't even remember the sequence, so we'll just go through HSO3. Sometimes you'll just see it with water. You just kind of need to know that that reaction does continue to an end result. Okay? These secondary reactions are usually used to cleave these odd elements off of your structure. So if you look at a reagent sequence that is like, I don't like, why is that atom on there? You probably need a second step. Okay? You are responsible for knowing that second step as reagents. In most of those cases, however, you're not responsible for the mechanism, okay, which is kind of nice, but at the same time, you then don't see that in class. So if you're interested in looking at those secondary mechanisms, talk to me after class and we can kind of go through and look at them. Okay? But it does kind of mean that when you see those reagents, you'll probably have to memorize the end results of those, okay? Because you've already now tied these reagents to electrophilic addition, you should hopefully have some hints to help kick you along that path. And with that, we'll end just shy of 40 minutes. Thanks for listening in. We'll look at details of these reactions in lecture.